All right, 3, 2, 1, off I go. Yeah, thank you everybody for listening to this talk, in which I'm going to show you some of the result of our little numerical modeling exercise we conducted, and to show you how actually easy it was for us to generate a synthetic palaeo-bathymetry that didn't exist before. You can, by the way, access our paper using this QR code right here. And also the discussion I would like to have basically is it follows the result of our numerical modeling of tides in this epicontinental sea. So yeah, hopefully we can start a bit of discussion here. So yeah, why did we do this? So we are in Utah, and there is this Upper Jurassic formation called the Curtis Formation. You can see where this photo was taken on the western margin of the San Rafael swell right here. That formation, you have the log right here on the side, and it's color coded. So it's a triptych formation. You have a lower unit here in black, which is very heterolytic, thinly bedded with very tabular beds. Then you have this dramatic facies change here, where you lose all the fines, you also lose the bedding, and you're left with basically amalgamated cross-stratified sandstone. And as you walk up this section here, you can see that slowly the bedding comes back, and so do the fines, and then you gradually go into this continental deposit that belongs to the Somerville Formation right here. And this shallow marine unit was deposited here in the innermost part of the sea, and it was surrounded at the time by desert. So good segue from Guido's presentation. And when we look a little bit closer at the rocks, we see a lot of evidence that tides were active at the time of deposition, and we can see these at a different scale. We can see, for example, bidirectionality acting at the bar scale. You can see here the bars are color coded, and you can see here the direction of migration. We see also bidirectionality in at dune scale or at the ripple scale. We also see evidence of waxing and waning of the flow. For example, in this tidal rhythmite, going from flazer to wavy to flazer bedding. We see also at the bar form again, with the bar, the foresets getting thicker and thinner and thicker and thinner in a rhythmical manner. Or is here as well with a rhythmical arrangement of these tidal bundles, with each bundles getting thicker and then thinner. And we also have other beautiful tidal bed forms, like these compound subtidal dunes here. So we have field observation that indicate tidal processes. If you want know more about the detailed facies analysis and all this kind of stuff, you can just Google Curtis Formation Utah, and you should be able to find some of these papers. And also another paper showing that tides were active at the deposition is not with regard to the Curtis Formation. It's actually some slightly younger rocks, but still related to the same shallow marine system. It was published last year by Holland and Wright, and you can, this is the title of the paper here. So we do have these tides, or field observation suggesting the tides were active at the time of deposition. But again, zooming out a little bit, this is the paleogeography during the Upper Jurassic, during the Oxfordian. We have this, shallow epicontinental sea, the Sundance Sea connected to the Pacific Ocean by this narrow corridor, and then you have this Curtis Sea right here. Now, and I said before, surrounded by desert. So basically, when we look at the contemporaneous desert deposit, we see no evidence of perennial fluvial input in these areas. And also there is basically no wave action. So we are in a tide-dominated environment. So this is what the rocks seems to tell us. But our question is, given this paleogeography, could tides actually really propagate that far into the sea? And so what we did, we generated this very simple Python code that allowed us to extract a depth from this map from Blakey. And basically, we selected the red band of this image, and we gave a depth to each pixel, basically. And so it should be the darkest, but basically the pixel which is the whitest on this map was always 0, so always 0 the coastline, and then we varied the darkest pixel on this map, which is around here, and we generated 9 different synthetic physiographies, and then we had this file and we generated these depths in the software. So this is a synthetic XYZ bathymetry, if you want. And then we use this bathymetry in the software called Del3D by Delta-Res, which is open source, and we forced it with an M2 tidal constituent. We didn't model any other tides because we wanted to stay make as little assumption as possible. but it allowed us to simulate the amplitude, the speed, and the basal shear stress. We also tested the sensitivity of the model by varying the initial tidal forcing from a quite realistic tides, so 0.5 meters at the mouth of the system, to extreme tides of 2 meters at the mouth of the system, just to test the sensitivity. And we also tested the sensitivity by varying the initial value of the bottom drag coefficients. We didn't change the coastal geometry, again, because we didn't want to make too many assumptions. We know that the coastal geometry would have a huge impact on the propagation of tides, but again, trying to limit the number of assumptions to make, we stick with the coastal geometry that was available to us. And these are some of the results. We have a continuous record of the tides for 3 to 4 months, depending on the simulation that was run. And you can see here this example of how the tide was propagating into the corridor and then generating this rotating amphidromic point. And then that amphidromic point basically smash a wave into the Curtis Sea. And you can see that the Curtis Sea is high tide and then exit low tides. And this is a map of the maximum water level. It's like a long exposure photo or this pin art version of the water level. Basically, every time a tide throughout these cycles reach a maximum level, it's recorded in this map. And you can see again here this amphidromic point right here. But basically now when we plot these results, we have three plots here. We have the tidal amplitude versus depth, the maximum flow speed versus depth, and maximum bed shear stress. And on the left axis is always the depth of the Curtis Sea, so the depth right down here. And then on the the other vertical axis here, it's the maximum depth of our system, so the deepest point in our system. And our results show a few things. The first is that certain paleophysiographies lead to an overall amplification of the tides. You can see the initial tidal forcing here is always 0.5 meter for all the simulation, but sometimes the tides are very much amplified and sometimes they're very much dampened. And the second thing that our results show is that you have the apparition of additional tidal harmonics in part of the basin, but they're absent in other part of the basin. And finally, we can use the simulated bed shear stress to look at sediment trend. And so these are twice the same map, just varying the vertical scale to highlight what's happening in the bottleneck. The green, our geological set point that we will talk about later. But what you can see in this map, you have the highest values and the bottleneck. So the coarsest sediment can be expected here. And then we can expect a fining towards ascendancy and also a fining towards the innermost part of the Curtis Sea. So basically, the first result is that the first conclusion, the change in paleophysiography dictates where and how much tidal amplification you have in your basin. Now, comparing it to field data, again, we are in Utah looking at this innermost and at rocks that were deposited in this innermost part of the sea. So this is a bit of a complicated slide, so just bear with me. I'm going to walk you through it. So this figure here is it shows the maximum extent of the Curtis Sea with a rose diagram showing the back and forth or the paleo current direction. And then here, this is a superimposed map of the maximum simulated bed shear stress. And you can see again these grain size, classes, boundaries, which here in the table. And here you have the actual geology. These are logs. They're color coded. Green is basically mud. Gray is sand. Gold is conglomerate. And red here is another type of sand. And if we focus on the one with a red label here, this cross section is just this one. So our model basically suggests a fining and then again slightly more coarser sediment towards this part of the coastline. And we go back to our data, what we see is we have an increase in green color, so an increase in mud, and then again you can see gray color coming back in, so again an increase in sand content towards here. So and then we focus now on this section right here, which is this one right there. You can see the same, the trends are there. It's not a perfect match, but the trends work. We see an increase in mud content as we go towards the south, which is basically what we can expect here. So we think that our model is validated by field data, and yes, tides can propagate that far into this epicontinental sea. And we think especially that the paleogeography with the 600 meters at the mouth of the system would probably be realistic, given how well it fits the fascist distribution. The model doesn't explain everything though. It doesn't explain what's happening, you know, in this brutal fascist change where we lose all the finds and everything gets very homogeneous. And also, it doesn't explain this bit of red sand here in the south, which we think was probably sand that was deposited by Aeolian processes and then subsequently flooded by the Curtis Formation and then reworked in these areas. Because again, this sea was surrounded by arid desert. And now, so the discussion I would like to have with you guys is, you know, the impact of these findings on sequence stratigraphy. So if we consider a very simple schematic bigrading succession here, coarsening up and fining up, which reflects basically an increase in energy and then followed by a decrease in energy, which could be an increase in tidal amplitude, bed shear stress, or speed, or all of them together. And so yeah, we have this graph here, tidal amplitude versus depth, and we can use now these, you know, different paleophysiographies as a proxy for relative sea level. And this is always the same initial tidal input of 0.5 meter. And you can see that, you know, again, given certain physiographies, you have the appearance of these optimal tidal amplification windows, basically, right here. And so the question is now trying to find which are the relative sea level curves that generate this specific energy pattern, you know, of increase and decrease in energy. And the first one would be a constant relative sea level rise. You know, I enter my tidal amplification window and I exit it. Or a constant relative sea level fall, or a fall then rise, or rise and fall. All of these four scenarios would all lead to the same energy curve, basically. And if we add again sediment supply, it will just add another possibility that can explain, you know, or lead to the same energy curve. You know, I have a constant relative sea level rise, but it's sediment supply that diminishes and then increases, meaning that I would have an increased water depth, and so I can again enter this tidal amplification window, and then I can exit it depending again on where you are with your A over S ratio. If you actually have a relative sea level fall or a relative constant increase in the relative sea level, but just slower. So yeah, we have a non-unique stratigraphy, meaning that one specific succession could have been the product, at least theoretically, by several relative sea level curves, and this is for one area of the basin. And you know, this red curve is from, let's call it area A. And then we have this green curve, this is for area B. And we saw that in area B, maybe you have these additional tidal harmonics, so these additional tidal amplification windows. Meaning that now if I have a constant relative sea level rise throughout the basin, you know, in area A, I will only have one bigrading succession, if you want. But in area B, I'll end up with having two coarsening up, fining up packages on top of each other. And you know, the question now is, so we have a non-unique relative sea level, meaning that, yeah, meaning a one specific relative sea level history can generate completely different succession in different part of the basin. So, you know, again, going back to sequence stratigraphy, you know, where's my flooding surface? How do I correlate these two packages? If you know, or you know, if this is what you have in your rock record, only this or both, you know, you'll come up with completely different basin history curves. So is it time maybe to integrate these internal tidal dynamic variations in our sequence strat model? I guess so. So to conclude, or to summarize, we've shown that the change in paleophysiography configuration will dictate where and how much tidal amplification you have in your system. And we've also shown how sensitive these tides are to relative sea level change or change in paleophysiography. And then as a consequence of this, we have a non-uniqueness of the stratigraphy and the relative sea level. So again, if you want to know more, we're soon resubmitting the revised version of the manuscript, which is pretty much spot on what I've just talked now. I quickly want to thank the Research Council of Norway for sponsoring this research, and my very amazing co-author, Professor Elisabeth Steele, and Ryan Mulligan at Queen's University, Professor Mattias Green at Bangor, and Dr. Dan Collins. So yeah, please don't hesitate to shoot me an email or social media or whatever. But yeah, I'm open for questions. Thank you very much.
That was great. Thanks, Val. Okay, so do we have any questions? Again, it's the same protocol, so type it in the questions chat box or raise your hand. So let's have a quick look. I don't see anything so far. So I'm going to ask it one or two in the process.
Go for it.
So yeah, I suppose the first thing is so the model. Has it been used for other tidal dominated systems in the modern?
So the Delft3D is usually used for modeling modern estuaries or river systems. I mean, it's a Dutch software company, Delta. So they work a lot on different rivers that go into the North Sea over there. But okay, there is not that many people who've used this software to look at ancient palaeo-seas. And the cool thing with this, what we've done is that you can, if you have a paleogeographical map, you can play with it and you can generate these fake or not fake, these synthetic bathymetries very easily. And then you can play around and just look at, could tides, let's say now you're in, I don't know, Argentina, and you have people saying, oh, this rock is tidal, or some people say, no, it's not. And what you can do is, if you have a paleogeographical map, you can just say, well, let's just test if, given our current knowledge of the paleogeography, was this possible or not? So I think this is the first cool thing about this paper, is that you can, it's a very easy workflow to just test an hypothesis.
Yeah. Are you going to apply it to other, Sundance related units?
It's a bit hard because there isn't that many Sundance related rocks that are preserved. There are some, but they're deeper, so they don't necessarily. You have the red shale, for example, in Wyoming, but they haven't really recorded any trace of, they call it deep water mudstone, but you don't have a lot of evidence of tides in there. But there are a few other seas which we're going to try to use the same thing, and I will not say any more now. So I see that Anna van Iperen has a good question, Dan Tech as well. If you can take, yeah.
Do you guys
have a question, but yeah, you can just unmute yourself, guys. Now
yeah, sorry, I didn't want to interrupt. Shall I just ask the question then?
Yeah. Yeah, go for it.
Yeah, so I was, well, first of all, thank you for the great presentation, but I was curious because I think you have a publication about sequence stratigraphy of this stratigraphic interval, which you published before doing these modeling. Yeah. So I was just wondering, to what extent would it change your previous interpretation?
It wouldn't change much right now because the model had static shoreline, really. The next step of this modeling exercise, so let's say that the theoretical consequences of our modeling exercise still stand, and our interpretations still stand as well. But the next step would be now to integrate the various relative sea level variation that we have recorded in these rocks to see if this would change. And again, our model only explained the deposition of the lower Curtis. It doesn't explain the rest of the Curtis formation, which is again there is something happening in the basin which we don't know that impacted the hydrodynamic of the whole system. So there's still some work, but our interpretation, I would say, still stand so far. So yeah, hopefully it will. I think our field data was robust enough.
Thanks.
Dan?
Hi, Valentin. Thank you for a very nice talk. Lovely figures in there as well. So it's good to see. My question is about the log constraint on the distribution of the Paleo-Curtis Sea. Do you have any north of the northern margin of the interpreted Curtis Sea? Because I know you've got some outside of the extent on the southern margin, but it doesn't look like there's any on the northern margin. So I was just wondering, how confident are you on the width of the Curtis Sea, and how much uncertainty does that add to the model of the tides being forced through that gap?
Yeah, this is an excellent question. It's this is the extent of the outcrop. All our green dots are outcrop geology, and there is no more outcrops west. So west is in this direction now.
Oh, sorry.
Yeah, there is no more outcrop in this direction, and also there's some bits of Curtis outcrop that would be the equivalent of this. So we don't have much. I would say we don't have much control on this, and I'm not aware of any subsurface data of these areas that have mapped out the Curtis formation. So this is Blakey's map. We know that he's taken, a few artistic liberties here and there, but we have to deal with what we have, right? But it is a good question that the pure geological control we have is only this is what we have. The rest we don't really know, and it will dramatically influence, especially this bottleneck. If it turns out this bottleneck is not really a bottleneck, you won't have this fining towards here, but you'll have an increase in amplification towards the end of your sea. So it will probably change a little bit the facies distribution, basically.
Does that, in light of that, then could you possibly do some sensitivity testing on the geometry of the outline of the sea in order to say, like, if it was this wide, how much effect would that have?
This is kind of what the next step in the modeling is. Now that we have basically a palaeo-bathymetry, we'd have to add also the relief on the continental side, and to see that if we have a relative sea level, like if we keep the geometry, if you want, but if we flood these areas, maybe the coastline now moves to here, or if we have relative sea level fall, now maybe the coastline moves, halfway into this area. So this is the next step of this modeling exercise, is to have a dynamic coastal variation and see how this would also impact. It will dramatically impact the influence of tides, but the general trends would pretty much still be relatively the same.
Oh, excellent. Thanks.
Yeah.
Okay, so we have one final question from the audience. So this is from Ivan Spichala. If the traditional indicators cannot be used due to non-uniqueness, what indicators would you look for to attempt the interpretation of sequence stratigraphy in tide-dominated basins?
Well, this is an excellent question. I'm not sure I have the answer, but you definitely have the clay mineralogy. If it was clay that was, you can identify, brackish, flat floculate in a brackish environment, or deep water mud, or deeper water clay minerals, bioturbation index potentially as well. And again, if you have if you have marshes, that would be top of the notch. But if you don't have the full sequence all the way up to marshes, then just using, which was what you see in the industry sometimes, people just look at trends and be like, oh, coarsening up means deepening up in tide environment, and so yeah, I would think clay mineralogy could definitely be one of them to look for, to identify. Basically give more focus more more importance to the mud and the clay content of your system.
Okay, great.
Thank you very much for all the questions.